All right, we can start, I guess. Okay. Right. So, welcome back. I'm happy to introduce my colleague Subhojoy Gupta, who's been working at IISc for around 6 years. He's going to talk about the dynamics of the mapping class group on the PSL2C character variety. Over to you, Subhojoy.
Okay, thanks, Vamsi, and I'm happy to be part of this symposium. So this is the title of my talk, and I'll explain all the terms in the title. I'm going to talk about the mapping class group and the PSL2C character variety and the action of the mapping class group on it. And I should also mention that although this is a geometry and with some of the other categories that the symposium is covering, and I'll try to point those out as we go along. So let me start with the mapping class group. By the way, I should also mention this is joint work. At least the main result I'll sort of mention later on is joint work with Indranil, Mahan, and Junho, Whang. And also for simplicity, sort of keeping the talk simple, closed surfaces, closed oriented surfaces of genus at least 2, although as we'll see, our theorem is in a slightly more general setup where you allow surface to have boundary components. Okay? So the mapping class group of such a surface S is the group of orientation preserving homeomorphisms up to homotopy. So usually it's described as this quotient here, where look at this group of all orientation preserving homeomorphisms and quotient with the subgroup of those that are homotopic to the identity map. Okay, and this turns out it's a discrete group. And an example that will also play an important role later on is a Dane twist. That's an example of a homeomorphism of the surface to itself. And a Dane twist you do along a simple closed curve. Here I've taken this curve A here. And a Dane twist along A is a homeomorphism that twists around A. So you can think of cutting the surface along A and then gluing back by a 360-degree twist. And so that, let's say a curve B that intersects A once, as I've shown on the left, becomes this new homotopically different curve that I've pictured on the right. And so in terms of elements of the fundamental group, A remains fixed as a curve, so that remains the same, whereas B becomes B times A. Okay, and so that's the Dane twist. You can do it along any simple closed curve. And in fact, the mapping class group is generated by Dane twists along simple closed curves. And one can think of mapping class group algebraically as well. Of course, since the mapping class is a homeomorphism of the surface to itself, it induces an automorphism of the fundamental group. And this assignment, in fact, identifies a mapping class group with the group of outer automorphisms of the fundamental group. And so, in fact, you can think of the mapping class group as what it's doing is it's sort of changing the generating set of the fundamental group. It's also referred to as a change of marking on the surface. Okay, so that's like a quick introduction to the mapping class group. So let me talk about the other object in the title, which is the PSL2C character variety. So PSL2C is just SL2C quotiented with the center. And the PSL2C character variety is the set of all these homomorphisms, the representations of the fundamental group of the surface to PSL2C up to conjugation. So there's this quotient by the action of conjugation. And this quotient is not nice, it's not even Hausdorff, but it turns out you have to do this double slash, what is called the GIT quotient or categorical quotient. And then you do get a nice Hausdorff space. In fact, it's an algebraic variety. Okay, and then sort of a kind of indicated what this GIT quotient is. So you have to identify more points. You have to sort of identify so two representations the same. The closures of the conjugation orbits intersect. And if you don't like the GIT quotient, you can just restrict yourself to irreducible representations. And this quotient, the usual quotient by conjugation works for that. In general, I mean, every equivalence class has a semi-simple representation. Anyway, so the quotient gives you an algebraic variety of dimension 6G minus 6. This is the dimension you expect if you do a heuristic count. All the generators of the fundamental group, 2G generators, have to map to these 2x2 matrices and to satisfy the relation that you have for on a closed surface and so on. And so the number that you get is 6G minus 6, and that's the dimension of this algebraic variety. And it turns out there are two connected components. And so one comprises representations that lift to SL2C, as I've indicated here in this diagram, and there's one that comprise all the representations that don't. Okay, and I should also say that the reason why it's called a character variety is because there are some special functions. There's these set of trace functions of these characters which generate the coordinate ring, which sort of generate the ring of regular functions on this algebraic variety, and these are associated with any simple closed curve. You can look at the trace of rho of well, this is how the function is defined. I've taken trace squared here because we're looking at PSL2C and not SL2C, and I'll mention why in a minute. And anyway, so this trace squared functions, these, so once you know these characters, you actually sort of can you know the representation of these. These functions would also show up later in the talk. Okay, so the reason why we look at PSL2C and not SL2C is because connection with geometry, and because we know plenty of representations of geometric interest that arise which are representations in this PSL2C character variety, and one class of them are Fuchsian representations, which are actually representations to PSL2R, and these representations are discrete and faithful. Discrete just means that the image is discrete, and faithful is that the homomorphism is injective. Okay, and so here the connection of geometry comes about because PSL2R is also the group of orientation preserving isometries of the hyperbolic plane H2, right? And so the quotient by this discrete image actually gives you a hyperbolic surface. So these are sitting inside this PSL2C character variety, and these are like real points, some of the real points in this algebraic variety, but there are other ones which are actual complex representations as well, with mapping to PSL2C, which can be obtained by sort of perturbations of these Fuchsian representations, quasi-conformal perturbations. These are called quasi-Fuchsian representations. These also turn out to be discrete and faithful. And this time, PSL2C can be considered as a group of orientation preserving isometries of hyperbolic 3 space, H3. And so the quotient actually gives you a hyperbolic 3 manifold, which is topologically the surface times a real line, okay, or an open interval, if you like. Okay, so there are these lots of examples of geometric interest of representations in this PSL2C character variety, and some of the sort of the picture you can have in mind is that they all of these lie in the component of character variety that comprise representations that lift to SL2C. And then so there, in fact, these quasi-Fuchsian representations form an open set. There's a subset of all Fuchsian representations, which is sort of half the total dimension. And that's actually a copy of Teichmüller space because, as I said, these give you hyperbolic surfaces. Right, and the way I've drawn it this way is that these are all sort of non-compact, so these sort of all extend all the way out on the other side. Right, so anyway, so this is sort of the picture of this PSL2C character variety to have in mind. Well, what's the mapping class group action? Well, as I said, any mapping class phi will induce an automorphism of the fundamental group to itself. So the way that it acts on representation rho is you precompose the representation with automorphism inverse. So the inverse is sort of just there to make it into a group action. Sort of, I guess it's group action on the left. Anyway, so this is the action on the representation, and it turns out that this induces something on this on PSL2C character variety, so because just conjugation orbits go to conjugation orbits, right? So that's the mapping class group action. It acts by automorphisms of this PSL2C character variety. So these are biholomorphisms, if you like, and it's a self map of sort of the space to itself. So somehow the sort of natural question from the point of view of dynamics is, what do orbits look like? What is the dynamics of this action? Okay, so one reason why it's also interesting is that there is the dynamics. If you just look at Teichmuller space, which is this set of discrete faithful representations to PSL2R, instead of looking at all the set of representation PSL2C, and on Teichmuller space, this dynamics is nice. We know that this acts properly discontinuously, and in fact, the quotient is something that is familiar. It's the moduli space of Riemann surfaces. Okay, so MG, where G is the genus of S. All right, so sort of this is the sort of the PSL2R discrete faithful representation to PSL2R, and it turns out in PSL2C, the action of the mapping class group is also properly discontinuous on these quasi-Fuchsian guys. Okay, so this open set that is there, sort of perturbations in some sense of these Fuchsian locus that's sitting here, that's shown in white. And so there is this open set inside the PSL2C character variety where the action is nice, but the action outside this open set is very mysterious. And in fact, there's the conjecture of Goldman that this is from the 1980s, that the action of the mapping class group outside this quasi-Fuchsian open set is actually ergodic, so it's chaotic. So let me just quickly say what ergodic means. So ergodic actions are something you can define when the group action preserves a measure, and it turns out that so ergodic means that any invariant subset either has full measure or zero measure. So there's not a decomposition of the space into in positive measure invariant sets. So it's sort of this action really takes elements all over.
Sorry, with what measure are you saying?
Yes, I'll come to that in a little bit. So this is sort of the general definition. So the short answer is the symplectic measure. Okay. Is coming from the Goldman symplectic form.
Okay.
Yeah.
And do you mean on each irreducible component, or do you on the complement, or do you mean the whole complement?
Yeah, so there is one more component. As I said, this is one of the components. I'll just focus on this one. I think if I remember right, this conjecture is also about the other component, but for the moment, let me just focus on this component.
No, I meant that the action presumably doesn't mix up the components, right? So ergodic will mean each specific component.
Yeah, that's right. That's right.
The components are all preserved.
Yeah, that's right. So there are two components. So I'll actually ignore. So I'll just focus on this one.
The indiscrete one form additional components, right? Or maybe
no, not for PSL2C. So outside, that's right. So outside here, there are lots of indiscrete representations. There are also some discrete ones, and so on.
Okay, so I was mistaken. They're all connected up when you pass to PSL2C. They're only
that's right. Okay. Yeah. So there are conjectures also open conjectures about PSL2R representations, but I won't describe them.
Okay, no, I'm mistaken. Thanks.
Yeah. Okay. All right. So so that's ergodic, and sort of the canonical kind of example to have in mind is if you look at powers of an irrational rotation on a circle. So this rotation would preserve the Lebesgue measure, and this is ergodic. So yes, as Siddharth was asking, this character variety, PSL2C character variety, in fact, any G character variety for a Lie group G, where you look at representations of from fundamental group of the surface to G up to conjugation, has a measure coming from a symplectic form. This was defined by Atiyah Bott and Goldman. And so once you have a symplectic form, you can talk about the symplectic volume form. And that's one way of thinking about the measure. And it turns out the mapping class group action preserves the symplectic structure. So these are actually also actions by symplectomorphisms on this character variety. in any case, if you don't want to think about the measure, so one of the consequences of being ergodic is that there are plenty of orbits that are dense. So if the action on a space is ergodic, it means that almost every orbit with respect to that measure should be dense. So that, to give an indication of how wide open Goldman's conjecture is that I don't think there's an example of any mapping class group orbit that is dense outside QF of S. Okay, so outside this quasi-Fuchsian open set. Okay, so if the conjecture is true, there should be plenty of them, but I don't think there's one that's known. And the best result so far is this result of Michelle Lee from about 10 years ago, where she showed that the Fuchsian open set is the sort of largest open set on which the action is nice in the sense that it's properly discontinuous. Okay, so and there's some related results of Canary and Storm, who sort of analyzed the action on the boundary of quasi-Fuchsian space. That's also very sort of sort of an interesting space to consider. Okay, so but why did Goldman conjecture this in the first place? Well, he had shown that the action of the mapping class group on a different character variety, the SU2 character variety, is ergodic. Okay, the SU2 character variety is what I've described here. So representations to SU2 up to conjugation. This time you don't need all these GIT quotients. It's a real algebraic variety also. And SU2 is the special unitary group that I've mentioned here. It's a compact Lie group. And somehow there, I mean, the idea of the proof was that there's an action of Dane twists, sort of are used along with the fact that irrational rotations on a circle are ergodic, the basic fact that I mentioned. It turns out that this SU2 character variety is kind of has a foliation, or almost all of it has a foliation with circles, and Dane twists act by irrational rotations on the circle. Okay, and then this actually was generalized to any compact Lie group. So representations to any compact Lie group G, so G character variety, Previtt and Sheehan. So it sort of is ergodic there, but anyway, so the question is about PSL2C, which is of course non-compact. And so one can ask a different question. One can ask when is a mapping class group orbit finite? So it's sort of somehow the opposite end. So instead of talking about when an orbit is dense, you can ask when an orbit is finite and when it is bounded. And this is the theorem that, this is the question that we answer. This is the theorem that we proved. Well, I've only stated in the case of a closed surface when genus is at least 2. And this is the statement in that case. The mapping class group orbit of a rho in the character variety of representation rho is finite if and only if the image of the representation is finite, and it's bounded if and only if the representation is a unitary representation, conjugate to a representation. Then, well, since I've taken PSL2C, I guess it should be PSU2. Okay, and in both of these, sort of if and only if, so one direction is kind of easy, is if the image of rho is already finite to begin with, there are only finitely many matrices that show up in the image. Then when you sort of precompose with automorphism fundamental group, I mean, you won't change the fact that the image is finite, and so there are only finitely many permutations of those matrices possible. So and SU2, as I said, or PSU2 is a compact subset, and so if and things would remain inside that bounded subset if you act by the mapping class group. So one directions in these are sort of easy. It's the other direction that's hard. Let me make a few remarks. Well, first of all, we actually work with SL2C. Instead, I've mentioned PSL2C because of its connection with these geometric manifolds, as I mentioned. But our work is actually, the statements are actually SL2C, and our statements are also for surfaces with boundary and positive genus. And it turns out that, over here, in the statement I've written, you need genus at least 2. It's not true for genus 1. And I'll describe why in a minute. Okay, so the counterexample for genus 1. But we show that that's the only exception. Okay, so genus 1, you have something called special dihedral representations, which have finite, as was an infinite image, but finite mapping class group orbits. Okay, and so notice that I mentioned positive genus. It turns out it's false for genus 0. In fact, it's, I think, the full classification of finite orbits is not known for punctured or sort of n-hole spheres in general, except for the 4-hole sphere, where the finite orbits were classified in this paper. And in fact, this is where the connection with analysis comes in. These turns out these finite orbits correspond to algebraic solutions of the Panleve-6 equation. Okay, and there had been a lot of previous work by people who came up with examples of these finite orbits, etc. But these people kind of completely classified them. Okay, but that's just for the 4-hole sphere. So there, in fact, the statement, the theorem is false. So you do need, sort of positive genus. And you also, it's sort of interestingly, is false for the PSL NC character variety when n is very large. And this was also some fairly recent result, and building on work of Coberda and Santarubane, so sort of somehow PSL2 is also kind of essential here. Okay, so let me mention the sort of a counter example in genus 1. So this is it's called a dihedral representation. So here, genus 1, you just have a torus, and you define this representation by mapping this, this A curve to this kind of inversion, 0, 1, minus 1, 0, and B curve to this diagonal matrix. So of course, this would have infinite image because powers of B will kind of, sort of grow larger and larger in norm. And so this is an infinite image, but it turns out the mapping class group orbit of this representation is finite. And so let me try to sort of convince you of that. So you can try to sort of apply Dane twists along B. So it turns out sort of Dane twists around A and B, they generate the mapping class group of torus, which is SL2Z, in fact. So if you do Dane twists around B, so if you work out where these matrices sort of take you, so it's A, B to the power K, that's if I do K Dane twists around B. So it's the power of a Dane twist around B. So then this maps to this new matrix. So now the generators map to these new matrices. And you might be worried that, here sort of as K tends to infinity, these matrices sort of seemingly sort of diverge, but it turns out these are conjugate to this representation rho above. Okay, and this sort of conjugation is via this diagonal matrix if I've done my calculation correctly while preparing for the talk. Okay, so this is sort of an example of a counter example in genus 1. In fact, you can allow punctures here and or sort of holes rather, so boundary components here, and these are what we call special dihedral representations. It's sort of similar where there's one curve A which maps to this inversion 0, 1, minus 1, 0, and somehow the complement of that curve, your representation restricts to a diagonal representation. So sort of generators map to sort of diagonal matrices like happens here. That's what kind of roughly speaking what a special dihedral representation is. And this works only for genus 1 and not sort of higher genus because there are more mapping classes. So suppose, just as an illustration, if you take a genus 2 surface here, and I kind of try to do the same thing as sort of I map A and B. Well, here maybe I've interchanged these matrices. So sort of B maps to, so A and B sort of generators of one of the handles, and B maps to this inversion, and A maps to this diagonal matrix. And the other handle I just map to the identity sort of matrix. And so you define a representation this way. Then it turns out that, well, this is, of course, if you do Dane twists around B or A, as we did earlier, so then you won't, diverge in the PSL2C character variety. But there are other mapping classes, and then there are mapping classes that sort of mix up the handles like we've shown here. So maybe the yellow curve goes to this yellow curve. So I've written down where the generators A, B, C, D, go now. And there's still sort of two handles, and these pairs of curves, they intersect once. So there are these two handles in this second picture. This is sort of realized by some mapping class. And if you run computes where these matrices go, well, this time in the second handle as well, there is this diagonal matrix where this diagonal entries, one of them is positive and greater than one, right? So in modulus. And so now if you do Dane twists around C prime, this new generator in the second handle, then you would be producing matrices that diverge. And so you would be getting an infinite orbit. So somehow this dihedral representation counterexample only works for genus 1, possibly with these boundary, but not for the higher genus. Okay, but that's like just as kind of an illustration. But so let me say a little bit more about the proof. So a key ingredient of the proof was this theorem of Patel, Shankar, and Whang, which had some number theory motivations. Okay, so they were interested in a conjecture of Grothendieck cats, so the P curvature conjecture. Anyway, so this is the theorem that they proved. They showed that, well, here the surface you're allowed to have some boundary components. If a representation, suppose the representation has, maps every simple closed curve by one of S to a finite order element. Okay, so the finite order monodromy along any simple closed curve. So then they show that the image of rho has to be finite. Okay, and this somehow the proof also involves a little bit of number theory. And so the first step of the proof is to show that the traces of rho of gamma for any simple closed curve gamma is actually an algebraic integer. And sort of the first step, and then show that some of the Galois conjugates lie on the unit circle and so on. Okay, maybe there's more sort of topological proof of this, I don't know. But in any case, we can use this theorem. So sort of here's the flavor of the proof, and somehow it can be summarized by saying it's at least part of the proof that I'm going to talk about can be summarized as saying it's an analysis of Dane twists. So, what's the setup? So suppose you have a representation rho that has finite mapping class group, as a finite mapping class group orbit. To apply this theorem of Patel, Shankar, Whang, you want to show that rho of A has finite order for any simple closed curve A. Okay, so then you would know that the image of rho is finite as we want to show. So let's consider the case when A is non-separating. So this is sort of the picture here. So if you cut along A, don't disconnect your surface. So then you can pick a B which intersects A only once. And then the hypothesis about having finite mapping class group orbit implies that if you look at the traces of these curves as rho of A to the KB, which are the ones that you obtain when you Dane twist B around A, then these traces form a finite set, right? So because so these traces, as I said, form sort of the coordinates on this character variety. In any case, and so then you analyze what are sort of the different possibilities. So you compute what these traces are in a couple of different cases. So if rho of A was diagonalizable in this sense, if rho of A is conjugate rather to this diagonal matrix lambda 0, 0 lambda inverse, then if you compute these traces, this is what it gives you. If this has to be a finite set, this K varies amongst integers, then either your lambda is a root of unity, in which case that's what you wanted because you wanted rho of A to have finite order, or this rho of B looks like this some kind of off diagonal matrix. But this is true for any B which intersects A once, and it turns out that in this latter case, you can reduce to this special dihedral case, which is sort of handled differently. It's sort of handled along the lines of the example that I pointed out. Anyway, this is a case where rho of A was this conjugate to this matrix, but it could also be that it's conjugate to something parabolic element of PSL2C. Well, in here, I guess I should have done SL to C, but anyway, so you can sort of talk about this case separately, and once again, sort of somehow this analysis sort of tells you that gives you what you want. Okay, and then this was a case where this A that you started off was non-separating, but if it is separating, then you break your surface into two simpler surfaces, simpler in complexity, and so the proof is by induction, and there are these base cases of the one-hole torus and the two-hole torus, which have to be handled separately. And so that's like a flavor of the proof. So I guess I'm out of time, so thanks for listening.
Okay, thanks, Subhojoy, for the wonderful talk. Let's thank the speaker. And are there any questions?
Okay, I had a somewhat speculative question. So you quoted this theorem which says that if every simple closed curve has finite image, then in particular every curve has finite image, right? Now,
right.
It's very difficult in general to say what curves are simple and what are not. Do you know if there should be a meta theorem which says that if any algebraic property is satisfied by all simple curves, then it's actually satisfied by all curves, simple or otherwise? Or I suppose there might be a more precise, I mean, a slightly weaker statement would be that being simple is not an elementary property in the sense of logic. Or,
right. I mean,
Zara has worked in logic related. I don't know, he may even have such a. So that's what this theorem is saying. So in some sense, you would say that if you could have you can't tell apart simple. It's a sort of density, I'm saying, almost like Zariski density of simple closed curves.
Right. I mean, but I don't know how far this sort of generalizes. So for example, I mean, thinking about, things like length spectrum, right? So it seems, right, this is what, Ajay has also been dabbling with, but it seems that, if you have a discrete length spectrum for all simple closed curves, this doesn't necessarily imply that, the length spectrum of all closed curves is discrete.
It doesn't, meaning it doesn't.
Okay. So, well,
so that is a little bit different because that is analytical, and I mean it's a property of not individual curves, but they're
right. But for algebraic, I don't know. It's an interesting question. Certainly, I mean, the trace functions that was mentioned, I mean, those are defined on simple closed curves, and so finitely many of them actually sort of determine the representation. So I mean,
but what I'm saying is that a result should be that we know that it's hard to tell whether a curve is simple or not, though there are algorithms. No algebraic property should be able to tell apart a simple closed curve from a non-simple closed curve. I guess analytically you do have something which is that in the, or whatever, Anyway, I was just maybe I won't take up too much time speculating.
That's it.
We know that the boundary components correspond to simple closed curves, so there is some sense. But just this kind of theorem, is there a much vaster generalization is what I would guess, but I don't know.
Right.
No,
it's quite possible. It's quite possible.
Any other questions?
Just a comment. So this is sort of in some weak sense, it's substantiating this thing, the Goldman's conjecture, right? That at least if you can't hope to find bounded orbits, bounded orbits cannot be dense in any way. So,
right.
But why were you looking at this in the first place? It's, as you said.
Oh, this is sort of, this is a kind of a question on the opposite end of, like Goldman's conjecture, when we were more interested in building, sort of dense orbits, but even something like this wasn't known. And, so for example, Lubotsky had a question of whether you can have a faithful representation, might not be discrete, but a faithful representation which has finite mapping class group orbit. And that is ruled out by this theorem.
I
for
see.
instance. Yeah. So,
I see.
yeah. So, I mean, yeah, there were other questions, but I don't know what exactly it would say about the Goldman conjecture, but certainly, it would say that, you can't have, images, when the image is finite, then you can't expect, I mean, well, yeah, I don't know. I mean, yeah, it's probably not really.
Yeah, actually, it's not
eliminated.
related. Yeah,
Yeah,
in a
not
way.
related. Yeah,
Yeah,
it's,
right,
yeah,
right.
yeah.
Right. Any further questions? Okay, if there are no other questions, let's thank the speaker again.